All right, in this next video, we're going to look at integrating over general regions, so regions that are not necessarily rectangles. And in question 4, it says to consider the double integral of the function 3 plus 2x over the region D, where D is the set of all points x, y, such that y is greater than or equal to 0 and less than or equal to 2 times the quantity 1 minus x, and x is greater than or equal to 0 and less than or equal to 1. Okay, so let's first draw a picture of D. And for, notice the bounds on y. So if y is 0, we're just on the x-axis. And if y is 2 times the quantity 1 minus x, then we're on the line whose y-intercept is 0, 2, and whose x-intercept is 1, 0. So as we let y vary from the x-axis to the line, we're letting x vary from 0 to 1. Okay, so if you put all that together, we're really describing this triangular region here in the first quadrant. Okay, so now for part A, it says set up the double integral as an iterated integral in the order dy dx, and then compute this integral. Okay, so first want to just make a comment that if we're looking at the order dy dx, okay, we're first going to fix in x, so this is the outside variable of integration, and then we're going to let y vary. Okay, so y varies. So what I'm going to do up here in our diagram is, well, I'm going to fix an x, so choose an x between 0 and 1, and let y vary between its low bound of 0 and its high bound of 2 times the quantity 1 minus x. Okay, so now let's go ahead and set up our integral over here. And so for our y integral, okay, for the bounds of integration, right, so we're fixing this x here in red, and then y will vary from 0 up to 2 times the quantity 1 minus x. All right, and so now what we're going to do is think about, okay, stacking these vertical strips horizontally as we let x vary from its low bound of 0 to its high bound of 1, right? So we're going to fill out this blue region D with these vertical strips here, okay, as we stack from 0 to 1 for x. All right, so for the x variable, it's going to go from 0 to 1. Okay, so now the key thing to notice here, right, is that we now have a variable up here in our limit of integration. But now as far as the computation goes, this is really no different than what we've already been doing when integrating over rectangles. Okay, so we're going to integrate from 0 to 1, and then here I'm going to go ahead and compute the integral of 3 plus 2x with respect to y. And there, right, x is treated as a constant, and I'm integrating with respect to y. So in fact, both of these terms are constants. So I'm just going to get a 3y plus a 2xy. And I'm going to let y vary from 0 to 2 times the quantity 1 minus x. And then we have our dx. Okay. So now I'm going to go ahead and plug in these bounds of integration. And while it's not necessary, it doesn't necessarily hurt to emphasize, hey, I'm plugging these in for y. It's easy to get turned around, especially when you have variables now up in the limits of integration, but it's not completely necessary to include those labels. So let's go ahead and plug in. So I'm going to get the integral from 0 to 1 of, so 3 times y, which is for the upper limit, 2 times 1 minus x. And then I'm going to get plus 2x times that y, 2 times 1 minus x. And then I'm going to plug 0 in for y. Notice I'm just going to get 0 for both terms, so this is it. And also notice that this expression now that I'm left over with depends only on x. And this is the thing we're going to integrate now. Now do a little cleanup, and as a little side calculation, you can find this is equal to minus 4x squared minus 2x plus 6. All right. So integrating there, we're going to get minus 4/3 x cubed minus x squared plus 6x. And we're letting x vary from 0 to 1. So plugging in, we'll get minus 4/3 minus 1 plus 6. Plugging 0 in is going to give us 0. So you combine all that and you find that the integral is equal to 11/3. All right. So that is part A. And now for part B, it's going to be to set up the iterated integral in the reverse order. Okay. And so what I want to do now is say this, right? If I'm going to switch and say, let's now do the order, say dx dy, and I'll get rid of that. Well, now we'll first fix a y, and we're going to let x vary. All right, so now x will vary first. All right, so now what I'm going to do is up here in the figure here, I fix a y, so I choose number y between 0 and 2, and then we're going to let x vary from its low bound of 0 to its high bound of, well, this point on the line. And how do I get this expression for x? Well, the idea there is, look, we know the equation that relates x and y along this line, so all I'm doing here is just solving this equation for x to get this expression. Okay, so now let's go ahead and set up this integral. Okay, so if I'm going to switch the order, right, so now I'm looking at the order dx dy, x is going to vary from, well, 0 to 1 minus y over 2, and then we're going to stack horizontal strips as we let y vary from 0 to 2. Okay, so fill out that region D with these horizontal strips, and the rest of the calculation is very similar, so you may want to pause the video and work through it on your own and then check your answer. But again, x varies from 0 to 1 minus y over 2, y is varying from 0 to 2, and then we just compute that integral in the similar kind of manner. And of course, we still get 11/3 for our answer, right? So it agrees with part A. Okay. All right. Now, one key thing, okay, to point out here is that notice switching the order of integration, unlike what we saw with Fubini's theorem, the limits of integration now are far more complex, right? It's not a matter of just swapping out the order as well as the limits. We have to take great care now with regards to the figure and how the limits would also change when you change the order. So remember, I said Fubini's theorem only applies to rectangles, and this is a good illustration exactly of why that's true. All right, so now what I'd like to do is just pull up a general setup here. Okay, so I broke this up into what we call type 1 and type 2 regions. And so let's say our region D is like part A of question 4, right? So we have, say, bounds on y, and maybe the bounds are in terms of functions of x called g and h. So y is between g for the low end, h to the high end. Okay, and then x ranges from a to b. Okay, so if I want to integrate, say, in the order dy dx, so again, I fix an x, right, the outer limit of integration, the outer variable of integration, and then I'm going to let y vary from the low bound of g of x to the high bound of h of x, right? So those are the bounds of integration for the inner integral, and then we're letting x range from a to b. So think about stacking these vertical strips to fill out our region D here in blue. And then for a type 2 region, we're just turning things on its side. Okay, so now our variable bounds here in terms of are referencing x. So x ranges, say, from the low end of g of y to a high end of h of y. and then we're letting y range from c to d. Okay, so now if I'm going to do, say, a dx dy integral, right, x is ranging from here to here, g of y to h of y, so those are those limits of integration, and then we're stacking horizontal strips to fill out our region D. Okay. All right. Well, we'll see more examples of this in the upcoming videos. Thanks.